My name is Joel Andrews.
I'm Ethan Lee.
Melina Tongpan.
And I'm Sang-Kwang Lee.
And for our term project, we found an article entitled Fast, Brief, Practical DFA Minimization, written by Antti Valmari of Tampere University of Technology.
So in our paper's abstract, we have the definition of a DFA, with Q being the finite set of internal states, and then we have input alphabet, the transition function, initial states, and final states talked about in this course. Starting from Q0, we calculate the next state using input and current state, and if it ends at one of the final states, then we accept the string, otherwise we reject the string.
The minimization of a DFA has traditionally required programs that are complicated, and they take O and K log n time, where n is the number of states and K is the size of the alphabet. The author's goal was to write a shorter, more memory-efficient program with the accepted algorithm running in O n plus m log n, where m is the number of transitions.
Often in practice, DFAs are incomplete, meaning that not every state contains an outgoing transition for every label. The running time of suggested algorithm for DFA minimization has been the old notation m plus km log n, or another equation similar to that. It is possible to implement a complete DFA minimization program that removes irrelevant states and transitions that are not reachable from the initial state, or when no final state can be reached.
So one of the features of the algorithm is that the program can remove needless states from the DFA. And this is a snippet of the code that does that. Its running time is O, n plus m. So you see in there it has the functions remainder unreachable and reach, and those are the ones that cycle through all the states and block off the ones that are not needed.
So here we have a simple DFA that we're going to be minimizing. We have the number of states, the number of transitions, and then here on the right-hand side, you'll see that we have our start state, the transition, and then the end state, and we'll just have a string 001 that will be entered into our program, and then our program will prompt for state Q that are defined as final states.
In general, DFAs can be minimized efficiently with short programs. They are relatively straightforward to design algorithms for. The running time is O can squared, where n is equal to the absolute value of Q and K is equal to the absolute value of sigma.
So some uses of DFAs include vending machines, etc. And you can see those listed here. And as common as all of these uses are, if you add one useless state or transition to each of those objects in the real world, our world just slows down a lot. So the more condensed and faster our machines run, the more efficient we are and the more we can accomplish every day. So here are our references, and then we will now demonstrate our project for you.
So as Ethan explained in the previous slide, we're going to enter the actual the number of states first. So we got total of 5. The number of transition, we got total 8. The initial state was included as 0. The number of final state, you only had 1. And starting from here, we're going to enter the initial state, the transition symbol, and the end state. And starting on that, we're going to enter and here we're going to enter the actual final state, which is 4. And here are the results showing the new number of states, the transition, the initial state that you have, and the number of final states. The final state you're going to have is the state 1, and based on the string, which is going to show the initial state as 3, transition as 0, and the ending state as 0. If you keep the drawing, you'll have a shorter DFA.
All right, thank you very much.